Welcome to this class. So far we've looked at kinetics in different ways, right? We looked at the different orders. We looked from an analytical side, how to solve that, how to integrate uh, reaction equations, ordinary differential equations. Then we went through the numerics using Spider in the last couple sessions. And today I want to show something more about complex systems and systems chemistry. So one of the examples we did in the Spider class was to look at this logistic map where we saw already some oscillations. So that is a very interesting field that is actually a combination of different other fields. So let's quickly get an overview of this new field, which is recently now started, let's say in the last decade, which more and more people are being attracted to, and that is the field of systems chemistry. So what is systems chemistry? We start, let's say, at the smallest level, atoms and smaller. We're in the territory of physics. If we look at how to make molecules, and we can make basically any molecule you can imagine nowadays, we're in organic chemistry. Then in the last 5 decades, there was the new field at that time, which was supramolecular chemistry. So that's looking at what are the non-covalent bonds between molecules and how can we make structures, how can we chelate things to each other, how we can form supramolecular polymers. Then systems chemistry is more looking at networks of reactions and how these networks behave on the network level. And this can also involve supramolecular chemistry. It can involve organic reactions, light-driven systems. It's a very wide diversity of things that you can imagine. And basically, if we go from all the way the other end from living systems, and we go top down, and let's say this is bottom up. So we go from physics to chemistry, supramolecular chemistry, systems chemistry. So the top-down approach, there's already a field which is very well established, which is called systems biology. So there, people are, again, very similar to systems chemistry, looking at networks, at biochemical networks that exist in living systems, and trying to learn something about their function and how it works. So there's a big gap here in the middle, because here we're basically in non-living or abiotic world. Here we're in the living systems. So there's a huge bridge to cross, and hopefully systems chemistry can bring us a little step closer, but there's still much work to be done. Other elements that I won't touch upon that are important in systems chemistry are formation of compartments. So you can think about coacervates, liposomes, any way to localize components in different parts of your system. Growth and division, information processing, we won't go there, energy transduction and motility or mobility, and that all comes together in that field. So very interesting. This is a definition. You can read it later if you want. But basically, it's a merger of different fields that are older, right? So there's the field of origin of life, prebiotic chemistry that's trying to understand how life started. Like I said, supramolecular chemistry looking at how we can build more complicated structures. And there's a lot of theoretical chemistry going on, and I will start with nonlinear dynamics a little bit in this course. And it goes very much to the physics side. But basically at the interface of all these fields, we find a new field that is now called systems chemistry. So why is this so interesting? Because things get complex. And complex and complicated are two very different things, as we will see later in this class. So there are already some journals on systems chemistry. So there's the Journal of Systems Chemistry, and there's Chem Systems Chem, just two dedicated journals for the moment. But of course, other research is being published in the traditional chemistry journals. And I won't go through all of these, but these are a number of the topics that are related to the field of systems chemistry. Okay, so if you want to know more about that, you can go to these journals, or you can read some of the review papers that have come out in the past 5 years on this topic. So to complex versus complicated. So here you see a Boeing 777. It has a lot of parts, right? But its behavior is not complex, it's complicated. So we can, knowing all the components and how they fit together and how they work together, we can basically be quite confident that we know how that plane is going to behave. This on the left side, these are fire ants that are making a bridge and helping in this way each other cross from this leaf to the stem of a plant. And that's a complex behavior. It's complex. It comes from self-organization. Okay, so let's look at a definition. So this is just one definition, but a complex system is a network, right? That's why we are going to look at networks. And there's no central control. So there's not one captain ant that is shouting, hey, everyone, we have to cross here, so let's make a bridge. The system, in this case, self-organizes to make this new function. And this can happen here. You would maybe not be surprised because ants are already living, so already quite complex. But you can have abiotic systems that show self-organization and emergence. So that's the the other property, is to get emergent behavior that typically occurs at a length scale and a time scale that is much bigger than that of the individual component. And the component can be a molecule, can be, in this case, an ant or a bird or anything. And so once you have a complex system, typically this only happens far from the thermodynamic equilibrium, then you can have self-organization. So this is not to be confused with self-assembly, even though in France these terms are sometimes used a bit as synonyms, but they're really not. So self-organization, and that can lead to very interesting and exciting things like information processing, adaptation, or even evolution, right? So Darwinian evolution is now also being found in simple molecular systems. Okay, but a field that is really a very strong influence here is that of nonlinear dynamics. And so in nonlinear dynamics, that's where people found chemical oscillators, and that was quite controversial. So the first observation really was in 1828. So Feichner was doing some electrochemistry, and he observed oscillating currents. Nothing much happened really for the rest of that century. Then came Oswald, who we saw in class 1, and he found periodic rates of dissolution of a metal in acid. So again, interesting, but nothing really happened until 1925, because in those cases, everyone said, well, you have a heterogeneous system, right? You have a solid or a surface, and you have a liquid, so there can be transport phenomena and there can be inhomogeneities. So no one really believed this until Lotka came, that proposed, this was a purely theoretical model that we'll see later in this class, that kind of already indicated that you can have oscillations purely based on the dynamics of reactions or reaction rates, even though this was a model for predator-prey and not a chemical reaction. Okay, so very important discovery by Belousov. He reported that there was an oscillating chemical reaction, homogeneous, so everything in the liquid phase. But unfortunately, no one believed him. So Jabotinsky, he had to come in. He improved the Belousov recipe a little bit, and that led to the very famous Belousov-Jabotinsky reaction, which is pretty difficult to really understand, but we'll show you some examples. But that really was the part when people started to get convinced, hey, you can really get things like spirals, oscillations, patterns in non-living chemical systems purely because of this nonlinear behavior of the system. So 1977, very important moment. Ilya Prigozhin, that did most of his work in Brussels, he got the Nobel Prize for non-equilibrium thermodynamics from the theory side, and he described what is called dissipative structures. So these are unlike self-assembled structures. These are structures that are only formed when you're far from the thermodynamic equilibrium, and typically they form on a much larger scale, length scale and time scale than the individual components. Okay, so let's look at the Belousov-Jabotinsky reaction, or BZ reaction, as most people call it, because it's pretty a long name, right? So the BZ reaction in a beaker. So we have stirring, and we add all the ingredients at time 0. Okay, they dissolve and they start reaction. Okay, here it's still a bit dissolving, but it will soon turn into a clear solution. And let's wait a little bit. So it's stirred, and there it goes. So it goes to transparent, and then the color comes back. It goes again to transparent, and it comes back, right? And for the BZ reaction, these oscillation, which are batch oscillations, right? So this is a closed, well, it's an open beaker, but it's a chemically closed system. There's no input or output of the system. So it's one of the very few systems that can actually oscillate in a batch system. So most systems have always an inlet or an outlet to feed in fresh reactants in the system in order to maintain the oscillations. Okay, so now we look at the same system, but in a gel. So we have a layer of gel here. You're looking at a Petri dish from the top, and this BZ mixture is there spread out in the gel, and it starts to react. And so what we get is little dots that are propagating outwards. And actually what the experimentalist did here is apply with the paperclip a little instability that then propagates. So you see that here you get spirals that start turning around, and this spiral state is actually taking over the whole system. So it's propagating outwards, and you get these spiraling systems that go all over the place, and they will eventually take over this entire Petri dish. So quite beautiful, and this is a purely chemical system. There's no living beings or any control mechanisms in here. So these are really dissipative structures, right? This is really on a centimeter scale. And the individual components are basically small salts. So they are incredibly small, but still can give rise to this very large scale ordering and temporal order as well, right? So space and time order. Okay, so very brief on thermodynamics. This is a movie of a number of cells that are imaged by confocal microscopy. They're rat fibroblast cells. And in this experiment, I accidentally put the laser of the confocal microscope way too high, so the cells die. So they go from this very complex moving cell to a soap bubble, a round bubble. So what's going on, right? So in the cell, as you know, we have the nucleus, we have all kind of supramolecular structures that are actually powered by chemical fuels like guanosine triphosphate, adenosine triphosphate. But when the cell dies, it becomes round like a soap bubble. So when you go to the thermodynamic equilibrium, it will try to minimize the surface free energy, and that actually dictates that that thing should be round and not so spread out and with little filaments sticking out and crawling around. So very, very basic, looking to the thermodynamics, right? So if we look at the Gibbs free energy, and we have the lowest point in the energy landscape, that's the thermodynamic equilibrium. If we look, there are other states, right? There are local minima. So this is a kinetically trapped state. So depending on the height of this barrier, right, on the activation energy, we know if this is on the scale of the thermal energy, so kT, then this state will be metastable, right? So it will slowly relax to the thermodynamic equilibrium. If this barrier is very high, then the system can be kinetically trapped for very, very long times, right? So this we call a non-dissipative non-equilibrium state. So non-equilibrium, because there's only one thermodynamic equilibrium. So this is not thermodynamic equilibrium, but it's non-dissipative. That means if you take a kinetically trapped system and I put it in an isolated vessel, let's say, so it's fully thermally isolated, there's no exchange with the environment. Let's say the environment is here and this is inside. So even if there's no exchange, the system will stay in this kinetically trapped state, right? So it can be very stable, but you do not need to put in any energy or new molecules that can react. So this is very different when you're in a dissipative non-equilibrium state, right? So now we have delta G in brackets because we cannot really talk about Gibbs free energy in an open system. So in this case, there's a hairdryer, it's blowing air, and that air is keeping this ping pong ball kind of floating in midair, right? So gravity wants to pull the ping pong ball down, but the stream of air is keeping it up. So there's an input of energy here, and that is maintaining this at a fixed point. So it's a steady state. And it's a dissipative steady state because we are dissipating electrical energy in the motor, which is heating up and which is producing this stream of air, which is also dissipated by viscous dissipation. And that's causing, as a result, this ping pong ball to stay there. And the interesting part now is if you change the power of this hairdryer, you can get an instability. So here you get a mechanical oscillation because the ping pong ball is losing its stability and it's oscillating. So we have found now an emergent property, which is time oscillation of this ping pong ball because we're driving the system with an energy input. So this is a dissipative non-equilibrium state, non-equilibrium because it's not in the thermodynamic equilibrium, and dissipative because we have an input of energy which is causing the system to become self-organized in time. Okay, so what was the problem when the BZ reaction came along? The problem was that people had a certain idea about what the concentration of these species would do. So you see the appearance of this brown color and then disappearance. So people were thinking that, let's say you have an equilibrium concentration and that you had oscillations that were crossing the equilibrium point, which has to mean that you go up and down in the free energy landscape. So actually, this is not the case. This is not the case, right? You cannot spontaneously go up in this free energy, at least not on the scale of completely forming and so forming and destroying some kind of colored molecule like the brown molecule. But what's actually happening is you're looking at the oscillations of an intermediate species. So let's say you have A goes to an intermediate and that goes to a product. And this intermediate species is the one that has color. So basically, I'm getting color, no color, color, no color, color, no color, color. So I do get concentration oscillations in this intermediate species, but overall, I'm just transforming my substrate to my product. So there's always monotonous decrease in the free energy, right? You see that this is always going down, and it's never, like in this situation, it's going up. So that violates the second law of thermodynamics. This is okay with the second law. So that's actually what's happening in this chemical oscillator. If you want to read more about this is an extremely good textbook that I highly recommend if you want to learn more about this field. Okay, so back to self-organization. So the first person to kind of use the word self-organization is Immanuel Kant, the very famous philosopher. And so this is the original German. I'm not so very good at German. So here you can see the English translation. And so something I would like to point out is he says a thing exists as a natural purpose if it is both cause and effect of itself. So that is interesting, right? So if we have a cause, usually we have an effect. But he says that you have cause and effect of itself. So he's implying that the effect also influences back the cause, right? So we can see there's already a feedback loop of information from the effect back to the cause. Okay, let's look a bit farther. Okay, so this is a quite long text, but what I want to point out, okay, is that he thinks that with artificial instruments or in artificial systems, so man-made systems, that would be the only way to get this kind of self-organized behavior, which now we know, of course, that that's not true, because as I just told you, you can have a chemical oscillator that makes organization in time or in space. So fortunately, the reality is a bit nicer than what Immanuel Kant thought at that time. Okay, so now we come back to this emergent properties. What is an emergent property? So this is a definition, one of the definitions. Okay, so it's important that this is not a fundamental property of a single element of the system. So if you have, for example, think about a rabbit, you need a male and a female rabbit, otherwise you will not get population dynamics. You need many rabbits in order for self-organization to work in that case, and to have emergent properties like oscillations in time, for example. And usually, as I said already a number of times, these emergent properties, so patterns or temporal organization or spatiotemporal, often occurs at a higher level of organization or at a larger scale, right? So for rabbits, as we'll see later, rabbits and foxes, organization occurs on a much larger length scale and time scale, so over entire populations. Okay, so what's the difference between deterministic and emergent properties? So in a deterministic system, you have only the cause that goes to the effect, right? So you do an action and that has a certain result. which is completely predictable. For example, like a watch or a clock has many components. It has many gears, it has levers, it has springs, it has all kind of things. And the result is that you can read the time, but it's not a self-organized property, because there's just, from all these levers and components, you just get one effect, and there's no feedback mechanism. And I can write simple equations that predict the behavior of this watch. Now look, for example, at this population of birds that is flocking around. So they're flying around. So you probably have seen this if you're in the countryside. So these are sparrows, and they're flying together, and they form these beautiful patterns, supposedly to scare off predators. And so again, they form an emergent pattern in this case. And there's no captain bird that is shouting, hey, let's all fly left or let's all fly right. So each bird looks at its neighbors, at the overall conditions, and that forms this flock of birds, which affects the individual bird. So there is a feedback loop between cause and effect, which is creating self-organization. And so this can happen at multiple levels. So we'll show you this example of rabbits and foxes that are flocking. And this is more philosophical. So some people think that if you have these self-organized emergent properties, that at higher levels stacked of these systems, you can have what eventually leads to life. But we'll leave that to philosophy. So let's come to the simplest example, what we already saw in the class on where we coded the logistics map. But that starts basically from a simple rabbit model. So imagine you have two rabbits. So the rabbits at a certain time is nt. So this is a difference equation. And so we say the number of rabbits at time t plus 1 is 2 times that at the previous time point. So we start with 2, we go to 4, then we go to 8, then we go to 16, 32, 64, 128, 256, and so on, right? So you have an explosive growth of rabbits versus time. But that's, of course, not a very realistic model, because the whole planet would be full of rabbits. So we come to our more realistic model, which is the logistic map. And so we have, again, number of rabbits, which is determined by the previous time point. And we introduce this factor R, which is this combination of the birth rate, the death rate, and the population pressure. So population pressure means if you have an island and the island gets full, then the birth rate will decrease, which makes a kind of natural stop to the system. So we take this equation and we start at a certain value. And if we have R equals 2, we have an increase in the population of rabbits. If we increase R a little bit more, we see that there are oscillations in the number of rabbits, which is quite surprising from just this equation, right? If you increase R even more, so to 3.99, you get something that looks chaotic. And this is called deterministic chaos. So let's plot the number of rabbits after some time, 100, as a function of R. So if R is smaller than 1, right? So this region, we basically have all the rabbits that die out. So rest in peace. Between 1 and about 3, you have one solution. So this means, the same as I showed you just before, we have an increase and then we have a stable population at a certain number versus time. And then here we get something interesting. You see that the solution splits into 2 points, right? So if we look for the same value of R, we have one solution here one solution here. So that means I can have two different states that are allowed versus time, right? And the solution can oscillate between those two states. Then if we look a bit further, there is again a bifurcation, right? Which is again happening at some value. And the number of bifurcations rapidly increases. So once we go to this regime, we basically have chaotic behavior. And here we will have oscillations between, so in this case, you'll have two solutions. In this case, if we're a little bit past the second bifurcation, we'll have 4 solutions. Okay, so that is the first bifurcation, after which you can get emergent properties like oscillations in time. And here you are in the chaotic regime. Okay, so let's see how we can code this up. So we start by loading the libraries. So we're going to use again import matplotlib.pyplot spt, and we're going to define function. So we do define, we call it f with nt and r as inputs, so number of rabbits at time t and this constant r, and we just return r times nt times 1 minus nt. Okay, result. An empty variable, nt is 0.1, r is 3.3, steps is 100. And we're going to use a for loop. For I in range steps, we're going to do nt the function, right? ntr result append nt. Then we make our plot. So plt.figure, plt.plot results. We don't need this, plt.xlabel, call it generation, and plt.ylabel rabbits. Plt show. Okay, so let's run this. And if we look at the plot, we can see a nice increase and then a stable limit cycle. So we see sustained oscillations that are not damping over time. So now you might think, okay, that's interesting, but rabbits are living creatures. They're already complex because of all the biochemistry going on inside them. They're already self-organized as a living being themselves. So does this also happen, self-organization, in abiotic systems? And the answer is yes. So here you see a very simple experiment. You see a Petri dish filled with water, and you heat it from the bottom and you don't heat it from the top. So if you have a small temperature difference, you just get conduction. So you get a linear profile of temperature. But if you cross a critical point, the system has to self-organize into these hexagonal cells. So here you you see in the experiment, the movie is starting, you see from the top that there's the emergence of these self-organized convection cells. So if you would look from the side, you have the, let's say, the hot region here and the colder region here. And if you have a packet of water, let's say in this region, it is warmer than the environment above, so the density is lower, so it wants to go up. And a packet of water here is more dense than what is below, so it wants to go down. And so you can imagine if all the water at the top wants to go down and all the water at the bottom wants to go up, they have to cross at some point. And that leads to the emergence of convection rolls that turn in a specific direction. And they, so in 2D, it would look like this because the next one will rotate in the opposite direction, right? And then in 3D, that leads to this hexagonal structure, which in this case is not perfect, but it theoretically should be hexagonal. Okay, so this behavior was described by Lorentz, and he defined a number of equations. So he defined 3 parameters, x, y, and z. So x is proportional to the intensity of the convection, so convection or not. Y is proportional to the difference in temperature between the bottom and the top. And z is proportional to the distortion from linearity. So here you have no distortion, here you have a bit of distortion, here you have the chaotic regime, very big distortion. So that we can express as ordinary differential equations. So dx dt is the Prandtl number times, so this is just a constant, Rayleigh number is a constant, and this beta is also constant. And the other ones are the variables, so x, or y, and z, right? So those are simple ordinary differential equations, just like the ones that we see in chemical kinetics. And we can code them up, as I will show you in a bit. But here I will show you some of the results. So depending on the Prandtl number, the magnitude of these constants, you can get different kinds of behavior. So let's say we would measure x, which is proportional to convection, in time. So for a given starting condition, we will get a damped oscillation, and then we will get a single solution. So we get what's called a steady state. So if we plot x, y, and z in a 3-dimensional plot, so we start here, and then in time we spiral into this point, into this steady state. If we now increase this Prandtl number and the other constants, we can get sustained oscillations. So x is oscillating in time. And actually, when you plot it, x versus y versus z, you can see that there's a 3-dimensional shape that looks like a saddle. And so this is called a limit cycle. So you start at the initial condition, the system goes around a bit, but as soon as it hits this shape in the what's called the phase space, this is called the phase space, then you hit this limit cycle, and then your solution will always stay on this cycle, right? So if you look at these oscillations in x, they also have oscillations in y and in z, and together they form this saddle shape. Now, the weird thing is if we go to the chaotic regime in this state, so if you would measure x, you would think, okay, this looks like totally unstructured information. But actually, when you plot that in a 3D plot, you can see this kind of butterfly shape. So we start here, the solution goes around, and it kind of zigzags around on this shape. So that is in nonlinear dynamics. Okay, this is just a detail, don't worry about this part. It's called a strange attractor. So it's a shape in your phase space that doesn't have the dimension of the phase space, right? So in this case, the phase space is three-dimensional, right? We have a box. We have three axes. And this shape is something like 2 point something something dimensional. So it's maybe 2.5, I don't know the exact number, dimensional. And so that's, it has a fractal dimension. So it's not 1, it's not 2, it's not 3, it's not an integer, but it's some number in between. So it's a fractal dimension. And that is called a strange attractor. Okay. So you can look up the bifurcation diagrams for this Lorentz equation, which can get extremely complicated with many bifurcations and complexities. Okay, so let's look briefly how we would code that up in Spider. And we're going to start with the libraries. Import numpy s and p. From scipy integrate. We're going to import ODE-int, right? That's the ordinary differential equation integrator. So that's going to numerically integrate our differential equations. Import matplot pyplot as PLT for our plotting. Okay, so Lorentz parameters and initial conditions. Okay, so I can set a number of things. So I'm going to set a sigma, beta, rho to 10, 2.667 and 28, and U0, P0, W0, going to set it to 0, 1, and 1.05. Okay, so then maximum time points and total number of time points. Okay, so I'm going to set T max and N, we're going to set 100 and 1, no, 10,000. I'm just putting these commas like this to save some space so the script doesn't become super long, it just stays clearer like this. So I'm going to define my function, which I'm going to call Lorentz, which has as an input x, t, sigma, beta, and rho. Okay, colon, enter. Then the equations, so u, v, w, I pack them in x. And then I'm going to say up is minus sigma times u minus v. Vp is rho times u minus v minus u times w. Wp equals minus beta times w plus u times v. And I'm going to return up, vp, and wp. So we're going to integrate. Oops, sorry, I'm going to put it here. T, we're going to make a linspace, so np linspace 0 to t max with number of steps n, right? And I'm going to integrate, so f is ODE-int. So I'm going to call the integrator Lorentz, that's my model. And then I'm going to give my initial conditions, U0, V0, W, 0, time, and as arguments, I'm going to give sigma, beta, and rho. Okay, so x comma y comma z is f. Okay, let's see what that does. Maybe we can save this for a moment. And let's see if this runs. It runs, gives an error. WO, okay, that should be 0. Let's run it again. Sigma is not defined because I made a typo. There we go. Now it runs and I have an output, so that's good. So that seems to be solved. So let's look at some plots. So let's make a figure, PLT figure, and X is fig GCA projection is 3D. Okay, we'll see later what that does. And then we're going to make a multi-colored line. Okay, S equals 10, C equals NP linspace 0 to 1 N. This is just for making some fancier plotting. Don't worry about this. For I in range 0 n minus S to S X plot X I to I plus S plus 1 Y I to I plus S plus 1. Color is 1, C I 0 alpha. And then we go out of the for loop. Going to remove all the axes so it's prettier. X set axis off. Okay, and then PLT show. Okay, let's see if that runs. And I have an error. Line 42. Okay, this should be a 0. Always a typo. So there you go. You have a very nice three-dimensional plot. Oh, which shows this nice 8-fold shape. Okay, so the last example I want to go into is spatially extended systems. So we saw before and in the other classes that we can write kinetic equations for simple systems. So this is the system, the Lotka-Volterra system that I mentioned in the introduction, which was really a turning point in nonlinear dynamics. So imagine we have this model, we have rabbits, we have foxes that like to eat rabbits, and we have grass, which is the food. So we look at the first rate equation. So we have grass plus rabbits gives 2 rabbits. We have a rabbit plus a fox, which leads to 2 foxes, and foxes can die out to dead foxes, okay? And they do that with the rate constant k rest in peace. And that leads to the following rate equations, right? So dr dt right, so rabbits are being produced here. So we have kr times g times r, right? And we have rabbits that disappear in the second step. So minus kf times r times f. And for the foxes, we can also write that. So foxes appear netto here. So we have kf times r times f and minus kr rip times f. Okay, so that is nice. But now if we want to see, okay, imagine you have a landscape and you want to see how these foxes and rabbits are kind of behaving in a real forest, for example. So let's see how we can do that now. So I would like to show you how you can do Brownian dynamics. So the implementation I'm using is called Smalldyne, and it's a quite easy simulator that you can download for free from this website. It has implementations for Mac and for Windows already pre-compiled, so the installation is relatively straightforward. I won't go into too much detail on everything, but I'm just going to show you a couple of examples. So the example specifically that we just discussed about is the Lotka-Volterra example. So I'll show you the code for that in Smalldyne. And so there's a number of things to set up, number of dimensions. The species are rabbits and foxes. Here in this part, we set up a box with certain dimensions, and P stands for periodic boundary conditions, a start time and a stop time, and a time step. You can define colors for the different species and sizes for the dots that it will show in the simulator. And okay, these are a number of settings. These are the reactions, right? So reaction 1, rabbit goes to 2 rabbits. So this is actually an autocatalytic reaction. It's a little bit different than we did it with grass plus rabbit, but the overall result is the same. Here, rabbit plus fox gives 2 foxes, and foxes die out with certain rate constants. Okay, so 10, 8,000, 10. Okay, so these are the initial number of rabbits, and that's basically what the file entails. All the rest is done by the engine of Smalldyne. So let me show you how that works. So in the command line, I will just run Smalldyne lot-volt.txt. It will run. I hope you can see this. Okay. So it will show the simulator. Maybe I'll do like this, a bit bigger. And so we can see that the rabbits are red and the foxes are green. So if there's a population of rabbits that's emerging, there will be a fast propagation of foxes that follows that. And you can see even some wave-like behaviors that propagate really. Look at here, you had a propagation from 2 sides into this population. So this is a quite easy way, wow, that was a big one, to set up Brownian dynamic simulation. So it's really a spatially encoded version of what we've been doing all through this course. So it's really has real kinetics and Brownian diffusion built into it. And it's in discrete entities. That's the nice thing about Brownian dynamics. You can, of course, use other methods like finite element methods that use volumes where you set up certain reaction conditions. But this allows you to really see individual species. So it can really anticipate and incorporate these kind of spatiotemporal effects. Okay, so in the small dyne simulation, we could see this very intricate interplay between rabbits and foxes in the landscape. If we extract these numbers from the simulation, we can see what you could visually already see by eye is that once you have a big increase in rabbits, it's followed by an increase in foxes. So every time you have that, you see this alternating population dynamics. And if we make a phase space or a phase portrait here, we can see that there is indeed a limit cycle. Now, it's not a very nice shape, right? Because we have noise, because we have this stochastics of the movement of the rabbits and foxes. So you saw in the simulation that the foxes, they move around by Brownian diffusion. So the results you get are not as nice as if you would just code up these chemical rate equations in Spider. You would get very smooth, nice oscillations. Here we get more noisy data because we take into account the movement of the individual species. So to convince you that this is actually interesting and useful, these are actual data of furs that have been hunted in Canada, I believe. And so it's not foxes and rabbits, it's lynxes and hares. So a hare is basically a big rabbit, and a lynx is also a predator like a fox. And you can see that there is also the offset, right? So we have first an increase of hares, so the prey, followed by the predator increase the year after. So we can really see that there is this kind of population dynamics, which was already captured by the Lotka-Volterra model. Okay, so this is what I wanted to show you for today, to put a little bit into context how you can get complex behavior, emergence of spatiotemporal patterns, waves that we even saw in the Lotka-Volterra system using simple kinetics. If you want, you can explore this Brownian dynamics package, small dyne, in more detail. It's not mandatory, of course, but now you have a good basic understanding of simple kinetics, how to code it up, and even include a spatial dimension using Brownian dynamics.